So we first of all seen what is a Savian. Then we have some concurrent Savians, all three concurrent Savians in the triangle, in given triangle. Then we get a typical product of ratios is 1. This is what the Sevas theorem, and we could prove that by two ways. One is discussed or shared by one of our friends, and here is another, a regular or a typical way. By just having the area relation, we could prove that. Okay. Then we come to, this is another way that what we had worked to prove the Sevas theorem. Then we come to the converse of Sevas theorem. Then we come to the converse of Sevas theorem. We proved it almost by method of contradiction, and there can be some another way, but it's okay that we have very nice idea. Okay, so we know it that altitude, median, internal angle bisectors, those are spatial Savians. So if we want to show the concurrence of, say medians, we can use the converse of Sevas theorem immediately. We can use the converse of Sevas theorem immediately. Similarly, if we want to get the concurrence of internal angle bisectors of a triangle, then also we can get the use of converse of this Sevas theorem immediately. So these are some typical and small applications of our Sevas theorem and its converse. Okay. Yeah. So then coming to the point that our next part is little bit typical now. I consider that all of us know little bit trigonometry. Let me know frankly that who is not acquainted with trigonometry yet. Just raise your hand. Don't take tension. Okay, you don't know anything about trigonometry. Yes, Mira.
Yeah.
You don't know anything about trigonometry?
No, I don't know.
Good. Bhagyashri,
Yes, sir.
you also don't know anything.
Yes, sir.
Okay, Simran also. Okay, no worry. Then Agalya. If my pronunciation wrong, please let me know. Okay, Karnam also. Okay. Yeah. Okay. Basically, trigonometry. Yeah, the word trigono. That is what try. Then there comes gono. Then there comes metry. Okay. So that is what a triangle's measurement. In fact, it is triangle's measurements. Okay. What is the meaning of that and how we are going to go to use trigonometry in our part, that we shall see. Okay. Yeah. Yes, Kirti, you want to say something? No. Okay. Okay. So I am not going to take a good session on trigonometry now. I would like to show just you the idea that how we can use trigonometry in our regular way. We are not learning exactly what trigonometry is. Okay. See, first of all, we are going to see the chain of right angles. Okay. Let this is ABC. Say this is PQC. Say this is RSC. Say this is TUC. Okay. It is clear that AB, PQ, RS, TU are parallel to each other. So basically, we first of all get trigonometric ratios. Then we express the trigonometric ratios as the functions, or we extend the trigonometric ratios for any angle. Now, initially, we are focusing trigonometric ratios for acute angles, but they are applicable for any angle. So that way of journey is little bit lengthy, how we achieve the next trigonometric ratios. Instead, I am going to just try to just tell you maybe many things without proof. If proof is necessary, then I can give you the idea of the proof, but I think not 100% proof. So if you find that, say, this angle as theta, alpha, beta, gamma, theta, delta, like we denote the angles. So suppose this angle is theta, then with respect to theta, the opposite sides are TU or say RS. So these are the opposite sides. Okay. These are the opposite sides. Being known that the triangles are similar, all those triangles are similar. Triangle ABC, similar to triangle PQC, similar to triangle RSC, similar to triangle TUC, and so on. So ABC, PQC, RSC, TUC, all these triangles are similar. Then we know their corresponding sides. Like say, suppose if I say AB upon BC, then that must equal to PQ upon QC. That must equal to RS upon SC. That must equal to TU upon UC. What I did, I actually took the opposite sides of, that is nothing but opposite side of theta upon adjacent side of theta. Okay. Okay, just you read the chat. Tanish has put something in the chat that if possible, you just put on your videos. Yeah, thank you. What I said, opposite side of theta upon adjacent side of theta. So these ratios are constant as the triangles are similar. I hope you all agree with this part. No one has any query in this. Okay. Similarly, we can have, say, the ratio of some sides like here. Okay, it shifted over there. Okay. That AB upon AC equal to PQ upon PC equal to RS upon SC, like that. So what we say, opposite side of theta upon hypotenuse. So in short, when we have such a chain of right angle similar triangles, then we consider any of its acute angle. And for that acute angle, with respect to that acute angle, we have opposite side, adjacent side, and hypotenuse is common. Because if I consider here, say, alpha, then this would be the adjacent side to alpha. This is alpha, this would be the adjacent. This would be the adjacent. So it goes like this. Okay. So in short, when we talk about, yeah, you can write some running notes at your own, that in right angle, in a right angled triangle, sorry. theta be any, or theta be its acute angle. Okay. So for such theta that we have the constant ratio that opposite side upon hypotenuse. Opposite side when we talk, then it is nothing but opposite side to theta. That side is nothing but opposite side to theta. Then it's reciprocal hypotenuse upon opposite side. Then we have adjacent side upon hypotenuse. Then it's reciprocal hypotenuse upon adjacent side. Then we have opposite side upon adjacent side, and its reciprocal adjacent upon opposite side. So there are three kind of sides. One is hypotenuse, which is common or constant for that triangle. And then we have opposite side to theta, and then adjacent side to theta. So it goes like this. Okay. We get such 6 different ratios, and there is no any more possibility to get 7th ratio. Then these ratios are named. These ratios are named. Remember, actually these are the ratios that is nothing but with respect to the angle of the right angle triangle. So the earlier case was like this to get the knowledge of right angle triangle, because many things are erected vertically, making 90-degree with the horizontal. So trigonometry helped a lot in ancient time till today. Okay, so these ratios are showing up the ratio of sides. Hence, the ratio of two quantities of same unit and the same quantities. Therefore, no trigonometric ratio has any unit because it is the ratio of two same quantities. Okay, but it has a typical thing, because as stated here in earlier figure, if this theta is constant, then the ratio, whatever the size of triangle, the ratio remains the same. Which ratio? Ratio of such typical sides with respect to theta. Okay, so we get the ratios as their names. This ratio we call it as sine ratio. This ratio we call it as cosecant ratio. This ratio is known as cosine ratio. This ratio is known as secant ratio of theta. This is tangent ratio of theta. And this is cotangent ratio of theta. Remember, these are the ratios of theta. These are not like any operations. These are the symbolic. And then the next steps in mathematics led us to understand these trigonometric ratios as the trigonometric functions. These are periodic functions. That is, after some typical value of theta, they take or they show the same value. They show the same value. Moreover, you get that there are some reciprocals of each other, like sine cosec, cosine secant, tangent, cotangent. But as human being always tries to be optimized, to optimizing the work. So these big names, sine, cosecant, cosine, secant, tangent, cotangent, must have some better abbreviations. Hence, the sine ratio is just stated as sine. We don't have to pronounce it as sin. Okay, so say sine theta. Here it is cosec theta. So only cosec. Then here cos theta. It is sec theta. It is tan theta. It is cot theta. Okay. I hope you got this. Again, I am claiming that we define now these ratios for acute angles, but it is not necessary that these ratios can show only the values for acute angles. We can extend the ideas to any angle of any measure. Even negative angle also we can work. That when we term trigonometric functions, we have a good freedom. We have a good freedom for that. Okay. So what are fundamental identities and what is the significance of trigonometry and all? That is not our cup of tea now. Okay, there are so many different relations among them. Okay, yeah, now the question comes, is trigonometry applicable for only right angle triangles? Then the answer is not, as we are able to apply trigonometry ratio for any angle. We can use trigonometry for that ratio's value in any triangle, but there must be uh, a thing to be clear. Suppose this is other than right angle triangle, and if I have theta, I can't call this as the opposite side. We can't call this as opposite side because it is not a right angle triangle. So in fact, trigonometric ratios are only because of right angle triangles, but they show some formulation or say typical things. So we term them as functions, because function is nothing but a working rule. There is a rule. By using that, we have some input, then that input comes with some typical output because of that rule. So we can formulate trigonometric ratios. Those formulations, nothing but the function. Okay. But initially, or to get the value, we always need right angle triangle. It is not that if we get here like the trigonometric ratios for in any kind of triangle, it is not correct to say. I hope you got this. But yes, if anybody wants the value of this ratio, we can have the 90-degree. Now this triangle is a right angle triangle. In that we can use the trigonometric ratio for that angle theta. Okay. So we extend the idea of trigonometry in our triangle, a general triangle ABC, general triangle IC. So in general triangle ABC, we apply the trigonometric thoughts. Okay. So coming to the point that, so I would like to ask you, those who don't know anything about trigonometry that we started today. So don't be here. Try to read, say from initially from textbooks, then from any different sources to have more knowledge on trigonometry. Don't rely on any person that he is going to teach you in detail. Try to get at your own. I think you can do that. Okay. So these trigonometric ratios have been proved, defined like this. These are the definitions. So till here, those who are unknown with trigonometry, I hope you must have uh, got some idea. If not, then ask me question related with this. Come on. Ask me questions related till here. Sin theta, cosec theta, cos theta, sec theta, tan theta, cot theta.
So why we call them as this type of names?
Just a minute. Okay, yes, please repeat your question.
So why we call them like opposite sides by hypotenuse? We
Okay.
call them in sine.
No, no, I didn't call. I first of all tried to show you that with respect to theta, we have three sides. One hypotenuse, which is always the same, that is opposite side to 90 degree. Then one opposite side and one is adjacent side. So there are three factors now: hypotenuse, opposite side, and adjacent side. Let's take two of them, either ABC. So you are taking ABBA, then BCCB, and ACCA. Like I have opposite side, hypotenuse, adjacent side. I took opposite side hypotenuse first. Then I took hypotenuse opposite side second. Then I take adjacent side hypotenuse. Then hypotenuse adjacent side. Then I took take that opposite and adjacent, adjacent and opposite. Then there won't be any more possibility. Only six possibilities are there. Then persons. So earlier legendary persons, many are unknown to us. They gave these names. They gave such names. Okay. So they define for theta in a right angle triangle. We have such all common ratios. And in this way, as here I drew this figure, according to this figure, we have any kind of triangle, but angle must be theta. These ratios remain the same because of the similarity. Then they have named like this. I hope Bhagyashri, your question is answered.
So, so why we particularly call them that the opposite side by hypotenuse is sine only?
Okay, because Bhagyashri Sahu's name is Bhagyashri Sahu.
So my question is why we can't tell the hypotenuse by opposite as sine
Yes,
and
because Bhagyashri Sahu can't be, uh, I think, Sagyashri Bhahu. Okay, that is what, just I'm kidding, or I yeah, means in funny way I can say my name is Bhas Bhamre, so Bham Bhasre. So we can't say like this. That why is it called as pen? The question goes like this: it is a pen, okay, stylus pen, that's all. Why is it called as stylus pen? I think, or otherwise when I say that this is a table, why is it a table? Like why opposite upon hypotenuse is sine? Those persons have defined and now it is accepted and fixed up. We can't change that. Okay, so names are given and we should use the same names. Okay,
so we can't prove them.
what
We can't prove them
what you need to prove?
that opposite side by hypotenuse is only with sine, not any other.
No, these are the names. These are defined names. Definitions can't be proved. Hmm.
Why? So how
Definition, I
can we
think.
say that the opposite side by hypotenuse is only v sine?
No, I think defined terms are defined. They are not conditional statements. Conditional statements to be proved, not defined statements. I hope you know this.
Yes, sir.
Ha ha ha. So these are the defined terms: sine, cos, then cosec, then secant, tangent, cotangent. These are the defined words. So it is just like that. Why? You can't prove that plus sign is only for no. You can't say that 2 plus 3 is equal to 5. Why? You can't prove this. Okay. And what Arushi stated that okay. Yeah, and Ritin say, yeah, we can. I think Arushi wanted to say that addition is an operation. Okay, but I wonder to say that in future you will learn, if you go for core mathematics, you will learn the uh, foundation of mathematics and structure of it. Then you will enjoy very critical things. Okay. Okay. So like say, suppose somebody says that -1 into -1 is 1. So why? -1 into -1 is 1. Why? So one can say that because minus minus plus in our school we are taught. But why? The question remains all. It's like, why can't we call algebra geometry? Okay, I think, see, many things are putting hands in hand. Like, we must thankful to Rene Descartes, then Lagrange, and also Euler. So many legendary mathematicians contributed to join the bridges or construct the bridges between these things. And then therefore nowadays we have very nice application of algebra also in geometry. But nowadays trigonometry can be considered as a very good tool or very nice tool in our classical geometry. Algebraic geometry is another part. Okay, algebraic geometry is very different part. Okay, so these are the defined things. I hope that no definitions can't be proved. Those are the names given, and hence, yeah, Mukund is supporting that. It is not something proven. See, undefined terms, defined terms, axioms. These are the pillars of any subject. On those pillars, we have so many conditional statements, which are the results. Those can be proved. Those are the theorems. So defined terms and axioms can never be proved. Axiom is nothing but self-evident truth. Axiom is nothing but a self-evident truth, which we can have its evidence, but we can't prove it, and which is obvious. Okay, so define, basically undefined terms are necessary. Because of undefined terms, we can erect some defined terms. Remember very well. And because of those defined terms, we can have the axioms. Then because of these three, some undefined, some defined, some axioms, we have very nice results. Those are called as either propositions or theorem, or say corollaries, or if it is observed that yes, it is true, but not yet proved, then conjecture, like that. I hope, Bhagyashri, you must have got your answer, or even if you want to ask, just go ahead.
Not so clear.
Okay, yeah, Mira, what you want to ask?
Yeah, is sin theta a ratio?
Sine theta.
Okay, yeah, sin theta is a ratio.
Yes. See, sine theta from this triangle, if you want, then it goes opposite side upon hypotenuse, like AB upon AC, or PQ upon PC, or RS upon RC, or TU upon TC, like that. Have you got it?
Yeah, yeah. So here we are saying that sin theta of two similar right angle triangles would be same.
If theta is same also. Yeah, if
Oh
triangles are
yeah.
similar, then it happens.
Yeah.
Yeah, you are right. Correct.
Oh yeah.
Yes, yes, Karunam.
So all the right angle triangles have the same ratio of, of any of the
Not all right angle triangles, if they are similar.
the values of all those sine, cosecant, and all that will differ from triangle to triangle.
See, sine ratio for one particular angle remains the same. It doesn't depend on the size of the triangle. Got it?
Yes.
Yeah. Any more question? See, actually, it takes a time to study about our trigonometry a lot. Yes, Mira, go ahead.
I have heard that sides of two similar triangles would be always proportional.
Hmm.
Is it right, or is it have anything to do with this?
Yeah, you are right. But if I consider any two similar triangles, then we don't have any fixed part. Like here in right angle triangle, we have fixed 90-degree, and so its opposite side as hypotenuse. And hence we can resemble those ratios uniquely. So we first of all found all possible ratios, and then those persons named them. We are following the same names, and we are not the authority persons to change the names. Okay. So if I say two triangles are similar, then the ratio of the sides are equal, correct? But those ratios can be the ratio of trigonometric. I hope no, unless they are in the right angle triangle or they possess such value, or otherwise not. Okay, I hope it is more than sufficient.
Yeah, thank you,
Yeah,
sir.
and yes, I'm not going to take some exercises on that. I would like to suggest, if you are ready to get that stuff. Okay, if you are ready to get that stuff, then we can. Okay, so Advait Pillai is asking to have the concept of negative angles. Okay, yeah. Uh, like, see here, I would like to tell you that first of all, angles are defined as the rotation of a ray about its origin in its plane. Okay, rotation of a ray about its origin in its plane, what I said. So consider a ray. Let's rotate this ray. Center is this. So it stops over here. From where I started is initial arm. Where I ended is terminal arm. Suppose my initial ray is OA and my terminal ray is OB, then this angle would be angle AOB. It is directed angle. Directed angle if sense of rotation. Sense of rotation is considered. When sense of rotation is considered, whether it is clockwise or anti-clockwise. Okay, when it is clockwise or anti-clockwise. So when it is clockwise, then the angles are negative. When it is anti-clockwise, then the angles are positive. So anti-clockwise sense is nothing but, yes, Advait, you have stated coterminal angles that are conjugate or coterminal angles. That is positive angle, and clockwise sense we have negative angles. So angles can be positive or negative. Moreover, in physics, angles are put in the supplement list of the fundamental physical quantities, because angles are really important in physics also. You must have heard about parsec. Okay, parsec. Okay. Oh, which voice come? I didn't understand. Okay, no worry. Parsec is nothing but like a parallax second that you can get information from the mail. Okay, so ASTC somebody stated over here. Yeah, we are going in depth. It's a little bit. ASTC, that is in a quadrant, that always we take the anti-clockwise sense where the terminal arm lies. Accordingly, the measure of angle happens. Like terminal arm lies in first quadrant or second quadrant or in third quadrant or in fourth quadrant. Accordingly, the measure of angle changes. In first quadrant 0 to 90, in second quadrant 90 to 180, in third quadrant 180 to 270, and in fourth quadrant 270 to 360. According to these measures, the values of trigonometric ratios of such angles are varying in sign also. So there is all silver teacups, all silver teacups. That
Or
is
add
what,
coffee.
yeah. So that ASTC and that somebody put. Okay. So I think we are having many things in trigonometry, but not in some kind of channelized way. We are looking here, there, here, but it's okay. Uh, Now you must not be confused about ASTC, so don't discuss more about that. Okay. You may learn or you can acquaint yourself at your own to get those things, and it is not that much harder to gain. Okay. So in short, you must have got what sine and what cos, what secant and all. I would like to request you to first of all get the exercises on trigonometry properly and then try to go ahead. But for today, let's come together because our main aim is really different. Just to a simple acquaintation, I told you this all, but I would like to suggest you by tonight, if you work on trigonometry, if you are not good at that, then I would like to suggest you first you go for school trigonometry, then come for high school, that is grade 11, grade 12 trigonometry. Don't jump to that. Okay. Go step by step. And if you face any problem, yeah, you are free to write me the mail. I shall answer in my capacity. Okay. Coming to the point. So our aim is really different for today. Okay. Now the case is that suppose I consider a circle. Okay. Then let's consider a triangle inside it. Now for easiness, I take such a triangle. But if this triangle is acute angle triangle or obtuse angle triangle, then also we have the same part. Okay. So you know what kind of the circle now what I had drawn. That circle is known as yes,
Yes,
Nitin. Yeah, it is the circumcircle, and its radius is known as the
circumradius.
circumradius of the triangle. Yes. So here we have A, here B, here C. So the length of BC termed as small a, length of AC as small b, length of AB as small c. Okay. Then we know that, sorry, angle BAC termed as capital A, angle ABC termed as capital B, angle ACB termed as capital C. These are the symbols which we use in trigonometry, also in our triangle geometry. Okay. Then circumradius is R. Okay. Circumradius is R. Let's show the circumcenter over here. Say O is the circumcenter. Then draw all those AO, BO, OC. What is your observation about AO, BO, OC? Can you tell me? What? Yes, Anushka?
They are all equal.
All equal.
Okay, they are all equal. Equal to?
The radius of the circumference.
Yeah, that is circumradius. That is nothing but circumradius. You should agree with that.
Yeah.
So as those all are equal, can I say that triangle AOB, triangle BOC and triangle AOC are equal?
Equal as in
No, sir.
Raise your hand and speak. Wait. Raise your hand and speak. Yes, Arjun.
So I think you can't say they're equal
Why?
because the bases are of different lengths.
Bases are different length or their included angles are different. Suppose I say that all are equal, what will happen? Who can tell? Raise your hand. Yes, Shrutika.
Sir, if all are equal, then the shape will be equilateral triangle.
Correct.
And the angles will be like exact.
Correct. Yeah, 120, 120, 120. Oh, then that
Yeah.
would turn to Fermat point. Oh, because we already had discussed for equilateral triangle. Okay, so coming to the point. You know that the alternate segment theorem or inscribed angle theorem, any name, both have the same statement. Who knows? Raise your hand.
it is also called tangent chord theorem, right?
Okay, tangent chord theorem is little bit different, brother of this theorem.
So could you repeat the name of the theorem?
Alternate segment or inscribed angle theorem. We
Yes,
have
sir.
learned. We have learned those who were there for RMOTP. Yes, Kanishk.
So is it that the angle at the center will be half of the angle at the circumference?
Angle at the center. Okay,
So
you
isn't
are
it the
Will be
referring
other
half
way
of-
around?
one person. Yeah, yes, Kanishk.
Angle is
Yes, the angle at the center will be angle at the center will be 2 times the angle at the circumference.
central angle is twice
Yes.
the inside angle.
Correct.
Yes, sir. He first
Yes.
said it the other way around.
Yes, I think Kanishk was in reverse manner he told. So I wanted to confirm whether he searched on Google is correct or not. Am I right, Kanishk? Okay,
Yes,
no
sir.
worry. At least because of this, you are searching, you are reading. Okay. If I was not telling the name, then how could you search? What is that? Okay, so this is what our benefit of technologies. Okay, coming to the point. Yeah, so angle BOC. Angle BOC would be twice of A. Angle AOC would be twice of B. And angle AOB would be twice of C. Any problem here?
No, sir.
Okay, so at least till here you are getting nice. Now I am going to drop the perpendicular from O to BC. Say it meets at A1. Okay. Can you tell me the significance of OA1? Just raise your hand. Significance of OA1. Raise your hand. Yes, Mira.
OA1 is perpendicular bisector of BC.
Of
BC.
BC. Yes. OA1 is the perpendicular bisector of BC. Okay, being perpendicular bisector, then so what kind of
Bisector. It is perpendicular because we have shown the 90-degree, but how can we say that it's a bisector?
Oh,
Because
Wait,
the
wait, wait,
radius
wait.
is
wait. Okay, Anushka Ram Rakhiani, sorry. Can you answer my questions? Okay, are you ready?
Yeah.
Do you know what is a perpendicular bisector of a line segment?
Yeah. So a perpendicular bisector will be a segment that is perpendicular to the line and it also bisects the line in two parts.
Sorry, you mean line or line segment?
Line segment.
Okay, sure.
I mean, it is okay. Line and line segment, they can be used. They both can make the same.
Okay, how can you make two equal parts of a line?
We can measure it and divide it into two parts, or
Okay, what
Being
is
a
the
line
length
is
of a line?
infinite, though.
Wait. What is the length of a line? Anushka,
I didn't get the question.
what is the length of a line? If I have drawn here a line,
The distance between the two vertices, the 2 points.
where which 2
Oh,
points
isn't
I
the line
should consider?
infinitely long?
Wait. Let her answer. Ha.
Okay, so you meant a line, right? That extends in both the directions.
So how can you find its midpoint?
We can't find the midpoint of a line.
Okay, so can a line have can a line have bisector?
No.
Okay, so in perpendicular bisectors definition, you told about line. I asked you about whether it is line or line segment. Then your statement was like that. It doesn't matter line or line segment. Now, what is your opinion?
Actually, I got confused. Like I didn't get what I was saying.
Okay, no worry, but I hope you got what is going on. Oh, nice, very good. Yes, so many hands are up. But yeah, now there is a very typical idea that perpendicular bisector theorem, that any point on the perpendicular bisector of a line segment is equidistant from the end points of a line segment. What I said, any point on the perpendicular bisector of a line segment is equidistant from the end points of the line segment. Means, suppose here I may draw that this is a line segment and here we draw the perpendicular bisector, say AB, then P, if any point, then we have PA equal to PB. Then converse of perpendicular bisectors theorem, that if a point is equidistant from end points of a line segment, then it lies on the perpendicular bisector of the line segment. Okay, so simply we use here as OB equal to OC. So O lies on the perpendicular bisector of BC. So when I drop a perpendicular from O to BC, it must bisect BC. This is one thought. Second thought, Bhagyashri just put that the perpendicular drawn from the center to a chord of a circle bisects the chord. The perpendicular drawn from center of a circle to its chord bisect the chord. So first way, by using the perpendicular bisectors way. Second, what she suggested. And third, earlier somebody suggested about the congruence of triangles. Arya, I think so, that triangle OA1B and OA1C are congruent. Therefore, we say that A1B and A1C are equal. In short, that what we say when we draw OA1 perpendicular to BC at A1. Okay, so we have BA1 is equal to CA1 is equal to A upon 2 small a. Why small a? BC's length is small a, so small a. And we have angle BOA1 is equal to angle COA1 is equal to A. Why A? Because angle BOC is 2A. Because angle BOC is 2A. So A. Okay, very nice. Then what? What is the next part? Yeah, we are coming up. So in short, we are getting over here that from right a triangle OA1B, sine of angle BOA1, sine of angle BOA1 is equal to, we are talking about this angle, opposite side BA1 upon hypotenuse OB. Okay. So what we are working on? We are working on angle BOA1. Look in the figure carefully. What is the measure of angle BOA1? That is capital A. So we have sine of angle A is equal to BA1 is half, OB is R, that is the circumradius. So we get here sine A is equal to A upon 2R. Sine A is that angle BAC. That small a is the side length BC. 2R, R is the circumradius. Okay. So we get A upon 2R is equal to sine A. What we got? A upon 2R is equal to sine A. Then similarly, from CO, or we say triangle CO1A. Oh, where is the figure? Let's check that figure. What I said, COA. Similarly, from COA, we are going to get, I forgot what we are going to get. Look in the figure. From COA, as here we got from BOC. Similarly, from COA, we are going to get something. Can you tell me what?
Sine B
where is
equal to B by
O1?
2R.
Okay, yes, you must need to raise your hand. Yes, Devanand.
There is it sine B equal to B by 2R.
Okay, so that goes like sine B is equal to B upon 2R. Okay, yes, Bhagyashri.
So where is O1?
O1.
You write here triangle CO1.
Oh, sorry. That is my mistake. No, thank you for clarifying it. Oh, nice observation. Oh yeah, really there is no one. Okay, I hope everybody got sine B is equal to B upon 2R, and also, and then what we are going to get from triangle AOB. Triangle AOB. Can you tell me? Just raise your hand. Triangle AOB. Just raise your hand. Yes, Mira.
C by 2R.
What? Mine or you?
Sine.
Sine. Sine of
Yeah.
angle Q.
C.
Huh?
Yeah.
Sine of angle Q.
No, sine of angle C.
Ah. Sine C is equal to C upon 2R. Okay, very nice, very nice. Oh, I really liked it. But what is the use of this all? Oh, they are separated out. They are not separated out. I just said. So if we have any issue that we get the sine angle in a right angle triangle, yes, but by that right angle triangle definition, because that is the definition, we can derive sine angle in our any kind of triangle. Note it clearly. That first of all I wanted to tell you. Okay, so sine we could find in any general triangle. Now because of these expressions, these means which? This expression, this expression, and this expression. We have something different. Yes. From that, I can write 2R is equal to A upon sine A. From here, I am getting 2R as B upon sine B, and 2R is also C upon sine C. This is known as sine rule for a general triangle ABC. Triangle ABC is our any general triangle. Note it carefully. So capital A, small a, capital R are all are well defined. They all are well defined things. Okay. So we need to go in triangle ABC only. I hope you got this all or not. Okay. So sine rule, how we got, everyone almost get it. And what I did to get the sine rule is nothing but proof of the sine rule. Remember, this proof is derived from the defined things. Sine ratio, define. Perpendicular bisector theorem. Okay, so what is perpendicular bisector of a line segment? Definition, like that. Okay, I hope you cleared this part, or do you have any question? One thing, whatever the kind of triangle be, it can be a right angle triangle, it can be an obtuse angle triangle or an acute angle triangle. This holds in general. Okay. Yeah, any question till here? No question. Very nice. Coming to the point. Okay. We have very nice. State and prove the trigonometric form of Seva's theorem. Wonderful. What is Seva theorem, master? Okay. If you have forgotten, I would like to ask you to just turn the pages of your notebook. Notebook. So we have to write this all. Don't say like this. We have to write it. Yes. You were writing. Yes. Then look in your write-up and find out what is Seva's theorem. So we are going to have now the trigonometric form of Seva's theorem. Okay. Let me draw the figure first of all.
Sir.
Yeah, who is there?
So this is Akshay.
Yeah, Akshay, go ahead.
Are we learning all this to prove the Fermat's point?
I think this is useful stuff, so I am taking up. Okay, you know this all.
No, sir. I am only new trigonometry till now out of all the points we discussed.
Okay, no worry, no worry. But this is, see, trigonometric form of Seva's theorem is again very nice tool. It is really a nice tool and it's converse also. So many times when we fail to find out the ratios, trigonometric form of Seva's theorem and its converse come to help us. Okay.
Okay, sir.
So these are good tools to go ahead. Moreover, uh, I want to show you that when we know that this is to use and this is to prove that our generalized result we have derived, and we are going to prove that in general way, not for constructing or by constructing equilateral triangle or only a square or only a regular pentagon in any general. So if in general it is proved, every part is proved. Then take theta as 60-degree, equilateral triangle.
Uh,
Take theta as 72-degree, pentagon, like that. Yes, Arjun, what happened?
sir, is Seva's theorem the same as the Menelaus theorem?
Oh, very nice question. Can you tell me what is Menelaus theorem?
So, because when I was reading about it, I read that it was the same thing. It was like uh, AF upon FP times BD upon DC times CE upon EA is always 1.
Correct, you are right. But there is a main difference. Who can tell me the major difference? Those who are knowing them. If don't know, then don't take tension. Yes, Anushka, go ahead.
Sir, Siva's theorem states that the extra condition of them being concurrent.
Correct, you are right. And about Menelaus?
Well, Menelaus doesn't have that condition, it just states that ratio. So Siva's states that if and only if they're concurrent, this holds true.
I think
Okay,
it
nice.
states something about collinear.
Yes, right, Janvi. And Anushka also tried very well that Seva's theorem tells us about concurrence and Menelaus theorem tells about the collinearity, but they both are equivalent. They both are equivalent. Yes, Anushka put the name. They both are equivalent. Note it carefully. So
But
we
sir,
can,
isn't being concurrent and collinear different?
yes, I am coming up because both are based on the first area relation. See, I would like to tell you very simple part. Whenever there is area relation, there is existence of some kind of ratios. Where there is existence of ratios of sides, there is existence of either BPT, basic proportionality theorem, or some kind of similarity. Whenever there is similarity or such kind of thing, we have the next ideas. Seva's theorem is because of the similarity as well as proportionate triangles in area. So because of area relation, we can get Seva. Because of area relation, we can get Menelaus. Or because of similarity, we can get both Seva and Menelaus or their converses. So in short, they are just the formulation of the next steps in similarity. Okay. So whenever there is an application of similarity, then it is must. Say for example, Seva. Earlier we proved Seva by using similarity. In that figure, we can smell Menelaus. Ah, so we can smell such things. No, master. Okay, okay. Okay, I would like to tell you that. Observe here ZRC, ZRXC. This point is X. Okay, what I said. And then see the triangle. This is a triangle. Okay, this is a triangle. BP extended. So here it intersects. Here it intersects. Here it intersects. Here it intersects with respect to triangle ABP. what I said with respect to triangle ABP. So RXC straightway, and we get the Menelaus in that. Just I want to tell. Don't go in Sevas and Menelaus. Okay. But I wanted to show you up such a kind of thing. Yes, Janvi, what you want to ask?
I just wanted to say, is it like a special condition of Seva's theorem? Menelaus theorem is like a special
Uh,
case of
yeah, these are special cases just because in Sevas, there is concurrence of three particular Savians.
yeah.
And in Menelaus, there is the collinearity, that three different points are there on the sides of triangle, as such that they are collinear. So that
Yeah,
is the
yeah.
speciality.
Okay.
That is the speciality. But that speciality is corresponding to the means concurrence and collinearity are putting hands in hand. Oh, but the same concurrence and same collinearity is not the meaning. Keep in mind. Means whenever there is Seva, we have Menelaus. Whenever there is Menelaus, we have Seva. Similarly about their converses. Okay. Yeah, coming to the point. You got the sign rule. Nice. Now we are in the trigonometric form of Seva's theorem. Okay. What is Seva's theorem? Three concurrent Savians must be there. Three concurrent Savians must be there. Okay. So trigonometric form. Yeah. Before going for trigonometric form, I would like to name the angles in some typical way. Okay. In some typical way. Say this angle is C1. This angle is C2. This angle is B1. This angle is B2. And this angle is A1. This angle is A2. Okay. So we should write now that given triangle ABC, then Savians AP, BQ, and CR are concurrent at X. They are concurrent at X. Okay. Moreover, we consider that let angle BAP is A1, angle CAP is A2, angle CBQ is B1, angle QBA or ABQ is B2, and angle CBQ, I think I'm wrong, ACR is equal to C1, and angle BCR is equal to C2. Dangerous. How we named those angles A1, A2, C1, C2, B1, B2. That is just because of our earlier Seva's theorem. And now we are having its trigonometric form. Then we need to prove that. We need to prove that. Okay. So sine of A1 upon sine of A2 into sine of B1 upon sine of B2 into sine of C1 upon sine of C2 is equal to 1. This is the trigonometric form of Seva's theorem. I wrote this intentionally in such a way. Actually, there should be some kind of, say, cyclicness, either A1, A2, C1, C2, B1, B2. We could go like this. Did you understand what I said? What I said now? Like A1, A2, then C1, C2, then B1, B2, again reaching here. That cyclicness, if we maintain, then we get the same. Just product is associative. So I did it like this, as well as distributive. I hope you got this. What about proof? Who can give me the idea to prove his part? Okay.
So we can use sine law.
Yeah. Oh. Proof.
So A R upon RC
Huh?
is, so for example, A R upon RB is sine C1 upon sine C2 upon sine C1.
Yes, go ahead, go ahead. Okay, so proof will go like this. From triangle, say ABP, by sine rule. By sine rule we have. By sine rule we have. I forgot what is the sine rule is. Okay, here is the sine rule.
Sine A is equal to A by 2.
Okay, sine A is equal to A by 2R. Or we have, yes, we can use that. But again, there are so many, what? Circumradii. Ara baapre. There are so many circumradii. Yeah, really. So we can get that sine of A1. Sine of A1 is equal to BP upon 2 A1, RA1. Just I wrote this. I am RA1. Why did I say like ABP's circumcircle? Oh, ABP's circumcircle. But is it necessary to get that circumcircle? I think, yeah, we can get that circumcircle. No worry about it. Or otherwise, we can have a different notation. What different notations of that? We are not getting it. Yeah, we can get like BP upon sine A1 is equal to AP upon sine B. Just check it. Just check it. We consider triangle ABP. ABP. We consider the triangle ABP. Okay. In that triangle, BP upon its opposite sine A1. Then AP its opposite sine B2. So we have that. Therefore, BP is equal to AP into sine A1 upon sine B. BP equal to sine A1 upon sine B. Okay. Those who didn't understand what I did, just ask me by raising your hand. Come on. What is happening if you are not getting up? Raise your hand.
So please repeat.
Yeah, Bhagyashree, I couldn't listen properly. Can you repeat?
Please repeat.
What you want?
Sir, the proof part.
Which proof? Only 2 lines are there. Ask me what you didn't understand.
BP equal to AP into sin A1 by sin B.
Sign, not seen. Sign.
Yes, so that's fine.
Okay. Watch here. Triangle and this sign rule. And this triangle. Watch it. And let me know where you are not understanding. Have you got? Small a is BC. Note it carefully. Is BC. Opposite angle A. Small b is AC. Opposite angle B. So A upon sine A is equal to B upon sine B is equal to C upon sine C. Like that. Have you got? Till here.
Yes, sir.
Now apply the same logic here. So BP upon opposite angle sine ratio. So BP upon sine A1 and AP upon sine B. The whole angle comes up. No. So that angle is B. Did you get it now?
Yes, sir.
Okay. Any more question? Any more question? Come on.
So it's clear.
Pardon. Yes, Anushka, what did you say?
No, sir, I told it's clear.
Okay. So similarly, and similarly. So many things we can be there. Okay. So similarly. We get CP equal to something, then CQ equal to something, then QA is equal to something, and then AR and RB. Okay. Okay. Look in the figure. How we got BP is equal to AP into sine A1 upon sine B. Go in the similar manner to get the next things. Complete them as fast as you can. Come on. Okay. Have you ever completed? What is CP? What is CQ? What is QA?
Sir,
Pardon? Somebody said something I couldn't get.
Sir, CP is equal to AP into sine A2 by sine C.
Yes, sir.
Yes. CP is equal to CP into sine A2.
I think it's AP into.
AP, sorry. AP into sine A2 upon sine C.
C.
Good. Yeah. Now I would like to ask some different persons who can give me for CQ. For CQ, look in this QBC. Yes, Abhivir, can you go ahead, dear? Abhivir.
Yes, sir.
Yeah, can you tell about CQ?
Sir, I haven't finished my calculation yet.
Okay, no worry, no worry. I would like to ask Dhwani. Dhwani.
Yes, sir.
Yeah.
I don't know if I'm correct, but I just gave it a try. I think it would be BQ into sine of B1 by sine C, I guess.
You are
Or
right. Don't take tension. You are right. Oh, I said earlier you are right. Just to save the time. Very nice. Very good. Okay, so you can go ahead. Nice. Yeah, Harini. Harini, can you? Harini, I think she must be unable to on the mic. No worry. Okay. Yes. Hem, can you? Hem,
yes, sir.
can you tell for QA?
Okay, 1 second, sir.
I try.
So can I try?
Wait. Okay. Indranil Menon. Indranil Menon, can you? Indranil Menon, can you? Yes. Okay. Okay. No worry. I think I only tell you because others will understand. Those who didn't understand that. But before that, I would like to see who are ready to answer. Okay, nice. The same persons are ready to answer, but it's okay. Try to listen me. How it works? Oh, 10 participants were raising the hand. That's really nice. So it shows that 11, 12, oh, yeah, 13. Let me say yes. I would like to listen from yes, Mrudula Anand. Can you tell about QA?
Yes, sir. Sir, I'm a bit doubtful about the denominator part, but I'll try. So I guess for QA, it would be QB into sine B2 by sine Q, I guess.
Sine B2 over sine A will come. The angle of the triangle.
Okay, sir.
Okay, yeah, I think you are right, but Q can't come because Q's opposite side goes AB. So instead of that, then there should come AB then. So that doesn't come. In that way also we can go because sine theta and sine 180 minus theta are the same. So in fact, here what I tried to tell you now, you look at A1, sorry. We look at A1. Okay, look at A1. Its opposite side is BQ. Okay, opposite side is, sorry, BP, I'm wrong. So we take BP is equal to, AP is here opposite to B. AP is opposite to B. So AP upon sine B. We need to take the angle of the triangle. So we took sine B. And then sine A1 because BP's opposite side is A1. BP's opposite side is A1. Similarly, when we come to A2, then A2's opposite side is CP. So CP comes. Then AP would be common as here opposite to C is AP. So we need to take AP then upon sine C and sine of A by 2 comes in multiplication. Similarly, when we think for CQ, similarly, when we think for now CQ, अरे यार,
So
yeah,
I
sorry.
think there's one more way to compute it. Like suppose you want to find for QA. Can you put the figure a little higher?
Yeah, just I'm showing up. Wait. Ha.
Yeah, so suppose you want to do for QA, you can look at triangle QAB, and A1 and A2 are like the only full angle of triangle ABC. So that will be the denominator. And then B2 is the small, like the half angle, like half an angle of the triangle.
Divided angle. Don't
Yeah.
say half angle. Ha.
Sorry, I meant divided angle.
Ha.
And that will be in the numerator. And you can see that the opposite side, not opposite, but like the other side of AQ in QA will be
Opposite
AB.
side.
Yeah, opposite side only will be AB.
Correct,
So
correct.
that's another way of computing it.
Yes, you are
not
absolutely
getting-
right. Yeah. And those are including the sides of the triangle.
Yeah. You can
And
relate it to the
yeah.
triangle ABC.
Correct. You are absolutely right.
Yes, sir. The sides corresponding to the angle have the denominator that.
Yes, but I started in this way, so I have to follow the same way. Okay. So that is also a simple way, but I started in this way. So, okay. Where were we? Okay, AR. When we are thinking of AR, opposite to AR is what? Sine of C1. So here CR into sine of C1. CR into sine of C1 upon sine A. And RB. What is RB now? RB is nothing but CR into sine of C2 upon sine B. Upon sine B. Yes. Now I am going to take LHS. I hope you got this all. So we are going to take now LHS. We shall complete this part. LHS sine of A1. No need. Then by Seva's theorem.
Sir, it couldn't be at C.
As?
The AR is at C into sin C1 by sin A.
Wait. I think I made a mistake somewhere. No, I think it is correct. What are you talking about?
Sir, I think so that PR
Which
will
one?
be at C. So AR and RB.
I think, yeah, for AR, there comes sine A here. And for CR, BR, here comes sine B. Okay. So by Seva's theorem, we have AR upon R1, RB, sorry, into BP upon PC into CQ upon QA is equal to 1. AR. What is AR? AR, CR into sine C1 upon sine A into RB. I am reciprocal and multiply simultaneously. RB would be sine B over CR into sine C2 into BP. BP, here we have got AP into sine A1 upon sine B into PC reciprocal, that is AP sine C. Sine C upon AP into sine of A by 2. Then CQ. CQ is nothing but BQ into sine B1 upon sine C into a reciprocal of QA, sine A upon BQ into sine B2. Okay. Is equal to 1. I hope you all have got this. Is equal to 1. Check what we can cancel out from numerator and denominators.
CR and CR.
Yes, CR, sine A, sine B,
Everything
sine
will
B.
cancel out, sir.
Yes, so there we get that sine C1 upon sine C2 into sine A2. Sorry, A1, I'm wrong. A1 upon sine A2 is into sine B1 upon sine B2 is equal to 1. That is equal to 1. And hence our trigonometric form of Seva's theorem is completed. Trigonometric form of Seva's theorem is completed. Okay. So we agreed that it works. Oh, yes. Now the fact we are going to use this. I would like to just show you up. We are going to use such kind of stuff. Just a minute. Oh, where is that figure? Let me check. Let me check. Just a minute. Before this, it is taking so much time to load. Oh. I think, oh yes, I got. Sorry. The figure is here. Oh, I forgot to show you up. Sorry. Yes, here it is the figure. So we need to show the congruence of these reddish colored line segments, and there we can use the tool which is known as the trigonometric form of Seva's theorem. How to use? Don't know. Now you have a time that you can think at home and just come to here to show what you have worked. Till then, we should say bye and see you because already we are running late. Okay.